So in this lecture, we are starting the new topic of balancing. Now, balancing first of rotors and then I think. Now, in any machinery, some parts move, often with accelerations. Now, other forces, which are joint reactions between two moving bodies, two moving links, they balance. So, forget about it. Now, what don't balance? The forces that some other link of the mechanism give to the fixed link, the frame, that may not balance. All of them may not balance. Now, under what condition they would balance? If all the links which are connected to the frame, if the frame forces and moments, which together is a balanced force system, then there is a possibility that the entire forces on the foundation or the frame balance. Even then, that is not a great thing to happen, because it may happen that one point of the foundation moves in one particular manner and another. I mean, one point on the foundation has one kind of force with respect to time, and another has another kind of force. Together they are balancing. That's also not a great fun. So the other way to look at is that if links of the mechanism move with accelerations, then whether in reaction to those forces you consider this body giving forces to other links which ultimately get transmitted to the foundation, or you see the corresponding inertia force and the inertia moment minus m into acceleration of the CG and minus j into angular acceleration of the body. If these inertia forces and inertia moments on the moving links you consider as the forces on the bodies and therefore on the mechanism as a whole, which finally goes to the frame, the foundation. And that way, these forces go to the foundation. And what is more dangerous compared to the forces and moments that are transmitted to the foundation in the case of structures is that here the forces and moments getting transmitted to the foundation are dynamic in magnitude and perhaps also in magnitude and or in direction. It may be that the magnitude is changing, or it may be that the magnitude is the same but direction is continuously changing. And this causes wear and tear of parts and joints, noise and vibration, and also damage to the foundation, the frame. And because of that, the building which is housing this mechanism, the machine, may also get subjected to vibrations and therefore damage. And those who have stayed near an oil mill or a floor mill or old style printing press where day and night sound goes on. I used to stay in that kind of a locality. It sometimes seems that the whole earth is shaking continuously in that region, and that damages the nearby. That damages that building itself. In the case of a building close to railway line, you would feel that. Now, right now we consider the balancing of inertia forces and moments on rotors. Okay. I think we will take up it. Now, what is the unbalance created by the rotating axis? Consider this axle mounted over these two bearings, and on this shaft or axle, a few things are mounted. One of them is this, the CG of which falls here, not on the axis. Okay. So, what is the acceleration of this? Acceleration of this is basically centrifugal acceleration, omega square, and therefore the inertia force is minus omega square e in the lower direction, and therefore towards, upward, as I have drawn this, upward there will be a force of magnitude n omega square. So that is the inertia force on this. Now, how to balance it? One possibility is internal balancing, in which you put another compensating mass in the same plane in such a manner that this mass and its eccentricity together balances this mass and eccentricity correctly. ME is equal to M prime E prime. Then you see that together the masses in this plane will have their CG at the on the axis, and everything is hunky dory. Okay. So this is internal balancing, in which you try to balance the unbalanced mass by putting an additional mass in the same. It can be balanced through external balancing also. You can put two balancing masses, one on this side and the other on that side, and both in the opposite direction. So, say you put M1 here, M2 here at eccentricities E1 and E2, and then you say that in such a manner we do the magnitudes we choose in such a manner that this is satisfied. See, omega square is same for everybody, okay, as long as we are mounted on this shaft. So, if M1 E1 plus M2 E2 together balance ME, then unbalanced forces will be zero. Unbalanced force will be zero. These two forces will balance this force. However, if only this is achieved, then what may happen is that, look at this, there will be moments of this inertia force, this inertia force, this inertia force. This moment will be this way, this moment will be this way, this moment will be this way. If there is a resultant moment about this point, about the axis perpendicular to the shaft, then what will happen is that an opposite, equal and opposite force will act here. So basically, in that case, one force will act here, another force will act here, and those two forces will form a couple. They are equal and opposite. These two forces will form a couple, and that couple at every instant will balance the resulting moment from these two together. These two are rotating, right? So their direction of forces will change. So all that can be avoided if the moments of these three unbalanced forces about this point is zero, and that will happen when the moments of these two will balance the moment of this directly, and that is this. Again, omega square is common. So this is called external balancing. When, in order to balance unbalanced mass, you put the masses, balancing masses in other ways, typically in two ways. Now, this is one mass electron, but we will see that even if there are more masses, you can do the same. Now, there are two standard terms here. One is static balance and the other is dynamic or complete balance. In the case of static balance, what happens is that the center of gravity of all the unbalanced or eccentric masses together falls on the axis of rotation. In that case, what happens? Since all the See, in that case, static balance. In the sense that against gravity, the shaft with its mountings can stay in any arbitrary orientation. You turn the shaft along with all its mountings by 20 degrees and leave it a little gently, it stays there. And at 10 degrees, it stays there. So, because in every case, the CG of all the eccentric masses together falls on the axis. So, and the axis cannot come down because the parts are rigid. So, by turning this way or that way, there is no chance of taking that CG further down. So, in whichever position, in whichever angular position you keep it, it stays there. When you keep it static, you position it and leave it gently. That is the sense of static balance. So, static equilibrium at arbitrary angular position. Now, during rotation, what happens? During rotation, all the resultant unbalanced forces will balance together. That will be zero. However, there may be a resultant unbalanced movement. What we were just talking about. In that case, the reactions at the two bearings. I mean, I'm assuming that there are two bearings, not more. Okay, but there could be more bearings. And in that case, there will be a distribution. The reactions at the two bearings at a distance L from each other will be the total unbalanced moment divided by the time. And the reactions will be equal and opposite with the rotating direction of force. And that is better because the bearing, the shaft itself will be subjected to continuous, hitting, digging, rubbing. I mean, which is not what. In comparison to that, you will have a situation where a constant weight is acting downward on both of them, and that's the end of it. Nothing else. That would be what you ask for, what you would want. Dynamic balance is said to hold when the center of gravity of all eccentric masses lies on the axis, as here, and resulting couple of inertia forces together is zero. In this case, it is called dynamically balanced or completely balanced. Obviously, when it is completely balanced, then the static balance holds anywhere, but only static balance is not. Now, we come to the real matter. In two-plane balancing, what we do, whatever is the number of unbalanced or eccentric masses, whatever may be their forces, individual forces, we try to balance all of them together by adding balancing masses into chosen planes. You can choose those planes where you want to put. Say unbalanced inertia forces F1, F2, F3 acting at axial positions X1, X2, X3, etc. So, from one of the chosen planes, say plane A and plane B. Say F1, F2, F3 are the unbalanced forces, and you have chosen plane A and plane B to balance them. In these two planes, in suitable locations, we will add suitable masses. So from one of those, you measure the axial position of different unbalanced forces. Take all them x1, x2, x3, and so on. And this point to that point, AB distance is set here. We are not taking bearing together, but just AB. Now, AB are the planes chosen for balancing. Now, equivalent unbalanced forces at planes A and B will be Found very easy. How? Say this F1. F1 can be replaced by one force here, F1A and F1B. One force here and one force here. So, in which F1A is F1 times this distance L minus X1 divided by this full distance. Similarly, F1B will be F1 times this little distance X1 divided by this full distance. Like similarly, you can break apart each force F2, F3 by their parts in plane A and plane B. Then F1, F2, F3 unbalanced forces will be replaced by a number of unbalanced forces here and another complementary set here. These are all in the plane. So their resultant you can find out their resultant in magnitude and direction. That will be in the plane perpendicular to that axis. In a parallel plane here, you find out the resultant of these forces here. So we have found these two. Now, in this plane, you put the balancing mass so as to get rid of this, and in that plane, similarly, you put one for the balancing masses MA and MB at eccentricities EA and EB. You put in directions opposite to these unbalanced forces. Thus, that this and this would. Vectorially, you could say that MAEA would be the sum of all these guys, inference that we created. And similarly, MBEB will be. And this is just like internal balancing in these two planes separately, considering these equivalent. So, vectors EI, EA, EB are in the transverse plane perpendicular to the axis. Now, several unbalanced masses in several planes can be balanced with just two masses, suitably placed in two planes. So that's it. Now, the process to do it. Most of the rest of this lecture you can actually derive. I will just take a little half-minute break and join you. Okay, so for the practical formulation to determine the balancing masses, supposing the unbalanced masses to be M1, M2, etc., at eccentricities E1, E2, etc., at several planes. Note that these eccentricities are vector because in the transverse plane they can be in any direction. Now we intend to add two balancing masses in two planes which we choose. Those balancing masses, call them M0 and Mn plus at the two ends. So far as indices are concerned, at least. They can be in that order also, but not necessarily. And eccentricity also we have to keep in those two planes. Now we denote the axial locations of the planes by x0, x1, x2, etc. up to xn plus 1. Now this x0 we take as 0, that is, we start the reckoning from the plane where we are putting this mass empty. Now what will be the force balance? Force balance will be this. that is all of the forces from 0 to n plus 1. So this will basically mean this thing into omega square, which is common. All that has to balance. All that have to balance. And the moment balance will mean the position, actual position of the unbalanced mass cross this force vector and sum of all those from 0 to n, which amounts to this. Here this q is the direction of the axis. This bracket should actually close. So we basically need to find out m0 e0 and mn plus 1 en plus 1 to satisfy these two equations. We can do it either by calculation or by scale. So the method is the same. You can do it, you can execute that method through calculations or by drawing. So let us see the calculation version. So denote the eccentricity with its magnitude and its direction in the transfer field. Then in that frame, you resolve the moment equation first. You will resolve the force equation also later, but moment equation has an advantage that here mi, ei, xi will be 0 because x0 is 0. So one set of unknowns go off so from the equation, so that is an advantage. That's why we first resolve the moment equation, all the cos components and then all the sine components. So in the cos components, one of the unknown set goes off, the other unknown set is left here, and these are all known. So you calculate this, and similarly you calculate this. Now between these two equations, you can determine the magnitude and the direction. Now this magnitude, when you determine, then xn plus 1 is determined by u. So you divide by that to get this. So one unbalanced mass into eccentricity in magnitude and direction we have found, because we have found theta and theta and theta. Now you go to resolve the force equations. Now these two being known, n plus 1 you take in this summation, which consists of only known, and on the other side these two components. And when you determine that, from there you determine the magnitude m0 e0 and the direction, and that's it. You are done actually, because you have got this product and this product. Now how to factor this product into m0 and e0, that's up to you. In that plane, in that direction, whether you put a particular mass at a particular eccentricity or put half the mass at double the eccentricity, that's up to you. And up to convenience of adding mass. So this you can do. I do. In some situations, if you find that putting additional mass there is a little difficult, then exactly from the exactly opposite location, you can actually take out that much mass. That will be sort of equivalent, as if you are putting a negative mass. So you can do that. Now, this is the calculation version. The drawing version, the graphical version. Here, make note that the force balance is a vector equation in n plus 2 vectors. Two of them only. Two vectors only one vector equation. Moment balance is also a vector equation in n plus 2 vectors, but by the reference that we have chosen, one of them is 0 because 0 is 0, and this you will utilize as we did in the calculation. So we start with that. But before that, make note that the moment vectors are basically rotated through 90 degree counterclockwise for positive side from the corresponding force vector. Keep it in mind and say that in all of your spoken and written discourse. But while drawing, you can draw them as parallel because then you will say that this entire moment diagram is actually 90 degrees physical. So first draw the moment pointer with the moment of the first unbalanced mass, second and third, first moment of the first unbalanced force, second one, third one, and so on. And that way you go this, 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 and then many others, and then finally this one, which in general does not close at the starting point. The closing one will give you the last, which is your thing that you are intending to put, which you want to determine. So this gives you xn plus 1, mn plus 1 into vector en plus 1. Divide this by xn plus 1 to get this. So 1. Now that you have got this, now draw the force pointer. Again, first one, first unbalanced force, second unbalanced force. Now, note that the second unbalanced force, all of them are in drawing parallel, but some might be coming anti-parallel. That is possible. If this x2 happens to be negative, then this will be this way rather than the other way, and so on. And then mn, en, and then this you have determined. Okay. This direction and this direction are not actually parallel, but I intended them to be parallel. Should have been anyway, whatever it is. No, it should be parallel. Mn plus 1, En plus 1 also you mark in that which you have just now determined. And then the closing side, this one, this dotted closing side gives you empty and that's it. So this is how you determine the balancing masses and the corresponding eccentricities by choosing planes in which you want to add them when the unbalanced masses are more. But how do you know them? For that, what we need to do, that we will discuss in the next.